Sorry. So this morning we have the second lecture of Jason Schweinsberg. So he's still talking about modeling the evolution of populations undergoing selection using branching motion. And just to say that Jason has kindly shared his slides with us. So the slides for the first three lectures are on the conference on the workshop website, like next to the talk underneath the abstract. And we'll put lectures 4 and 5 on later on. Okay, thanks very much, Jason.
Okay, thank you, and welcome to the second of 5 lectures on modeling the evolution of populations undergoing selection using branching Brownian motion. I want to begin with a very brief review of what we discussed in the first lecture. So we introduced some classical population models, the Wright-Fisher model and the Longrun model, and we showed that for such models, the genealogy was given by a process called Kingman's coalescence, where only 2 lineages merge at a time. We also saw some models with populations involving large family sizes. And for those models, we saw that the genealogy of the population is best described by a beta coalescence. In particular, the beta 2 minus alpha alpha coalescence describes the genealogy when the probability that individuals have k or more offspring is proportional to k to the minus alpha. Now, our main goal in these lectures is to understand populations involving selection. And at the end of the last lecture, I introduced 2 different models of populations involving selection, both of which could be approximated by processes that are based on branching Brownian motion. One of the models could be approximated by branching Brownian motion with absorption, and the other could be modeled by a branching Brownian motion process in which the branching rate depends on the position of the particle. So in this lecture, we want to introduce branching Brownian motion. I will begin just with a brief overview of ordinary branching Brownian motion without absorption. And I will describe the connection to the FKPP equation. I'll introduce some of the standard tools that are used in studying branching Brownian motion, such as the Manytotwo lemma and the additive and derivative martingales. And then I'll briefly summarize some famous results on the location of the rightmost particle in branching Brownian motion. And then I'll move on to the process that we want to study in much greater depth, which is branching Brownian motion with absorption. I'll explain how to make moment calculations for this process, and then we will discuss the case when the drift is supercritical and the case when the drift is subcritical. We will save the case in which the drift is just slightly supercritical, which is the most relevant for modeling populations, until the next lecture, and the case when the drift is exactly critical we'll discuss in the 4th lecture. So here is branching Brownian motion. So for now, we're going to begin with one particle located at the origin, although it's certainly possible to start from other configurations of particles. We will assume that each particle independently moves according to standard one-dimensional Brownian motion, right now without drift. And we'll assume that each particle splits into 2 particles at rate 1. It is possible to consider the possibility that a particle could give birth to more than one particle at a time, but throughout these lectures, I'm going to stick to the case of binary branching for simplicity. Here is a picture of branching Brownian motion. It was created by my graduate student, Jiaqi Liu. So we begin at time 0 with one red particle at the origin. It moves according to one-dimensional Brownian motion for an exponentially distributed time with rate 1. And then it splits into 2 particles, a red particle and a blue particle. They both move according to independent Brownian motions until they divide, and so on. And in this model here, particles never die, so the number of particles keeps increasing over time as we go in the picture from left to right. So I should have mentioned time here is on the horizontal axis and space is on the vertical axis. Now, a question that has attracted a lot of interest about branching Brownian motion is the question of where the position of the rightmost particle is located. And I'm thinking here of imagining looking at the particles lined up along the real line. And so by the rightmost particle, I mean the particle whose location is the maximum among all of the particles. So let's let R of t denote the position of the rightmost particle at time t. And we will let u of t comma x be the probability that r of t is less than or equal to x. So that's the probability that at time t, all of the particles are below x. And McKean showed that this function u of t comma x satisfies this partial differential equation here, which is known as the FKPP equation. And it was introduced by Fisher in 1937 and also independently at the same time by Kolmogorov, Petrovsky, and Piskunov. And the FKPP equation is known as one of the simplest partial differential equations that admits traveling wave solutions. And Kolmogorov, Petrovsky, and Piskunov showed that the solution to this partial differential equation with this initial condition is given by a traveling wave with a speed of the square root of 2. So in particular, u of t comma x is some function w of x minus the square root of 2 times t, where w satisfies this second order ordinary differential equation here. And as a consequence of these results, of this result, one can see that if m of t denotes the median position of the rightmost particle, then m of t over t converges to the square root of 2 as t goes to infinity.
Jason,
Yeah.
you have an initial condition, which is a step function. There you have inequality with the traveling wave.
I think you just need that as a solution.
So yeah, this is the initial condition at time 0. So basically, you know that there's a particle at the origin. So if you're to the if we consider x above 0, then we know that the rightmost particle is going to be below that, so it's 1. And
the point that another solution, not to recognize zero, is not the same solution because we don't have the same initial condition.
okay.
Or it's an asymptotic.
Okay, sorry. Yeah, that's intended. What they showed was that it converges to this solution. Yeah. Okay. Thanks. Yeah. Okay. And because this connection between branching Brownian motion and the FKPP equation is so famous, I want to briefly sketch an argument for why the FKPP equation arises in this setting. In order to compute the time derivative of the function u, we want to compare u of t comma x with u of t plus h comma x, where h is some small positive number that we're going to let go to 0. To estimate u of t plus h comma x, what we want to do is to condition on what the branching Brownian motion does after a small time h. Because particles are branching at rate 1, we know that with probability approximately h, the initial particle will split into 2 particles. The probability that the initial particle will split into 2 particles before time h is approximately h. And if that happens, then the probability that the rightmost particle at time t plus h will be below x is the probability that all descendants of both of the particles are below x. We know that the probability that the descendants of one particle are all below x at time t is roughly u of t comma x. And so by the independence resulting from the branching property, the probability that this happens to both particles is approximately u of t comma x squared. Now, the other possibility, which happens with probability approximately 1 minus h, is that there is no branching before time h. And in that case, we only need to account for the movement of the initial particle between time 0 and time h. And so let's let b sub h be the position of that initial particle at time h. And then the probability that the rightmost particle at time t plus h is below x is approximately u of t comma x minus b sub h, because the rightmost particle at time t plus h needs to be no more than x minus b sub h above where the particle started from at time h. Let's let wt be x minus b sub t. So w is Brownian motion started from x. And then if f is a twice differentiable function, we can approximate f of wh by a second order Taylor expansion. Taking expectations, the expected value of f of wh is approximately f of x plus the expectations of these two terms. But the expected value of wh minus x is 0, and the expected value of wh minus x squared is just the variance of how far a Brownian particle moves after time h, which is exactly equal to h. And so we can approximate the expected value of f of wh by f of x plus 1/2 times h times the second derivative of f at h. We can now write u of t plus x comma h as the sum of two terms. The first term takes into account what happens if there is a branching event before time h. So that's h times u of t comma x squared. And then we have 1 minus h multiplied by this expectation. And we can think of this expectation as being the expectation of a function of wh. And so from this result here, we can write it as u plus h over 2 times the second derivative of u with respect to x. Now one can just do some algebra and rearrange this, drop the term that involves h squared, and one arrives at u of tx plus h times 1/2 the second derivative of u with respect to x plus u squared minus u. And then subtracting u of t comma x from both sides, dividing by h and letting h go to 0, we get that the time derivative of u is approximately, is going to be equal to the right-hand side here, and that's exactly the FKPP equation. So I want to mention now a few tools that are used in studying branching Brownian motion, and I'll begin with a simple case of what is known as the many-to-one lemma. So let's first let B just be ordinary Brownian motion started at x. Then the random variable b of t, which represents the position of the Brownian particle after time t, will be normally distributed with a mean x and a variance of t. So it has a density given by this formula here, which satisfies the heat equation. The time derivative of p is 1/2 the second derivative of p with respect to y. Now, if we are working with branching Brownian motion, then the number of particles grows over time. And if we denote by n of t the number of particles at time t, we know that the expected value of n of t is exactly equal to e to the t, because each particle is branching at rate 1. And so the density for branching Brownian motion is given here by qt of xy, which is e to the t times pt of xy. And what I mean here by density is that if there is one particle at x at time 0, then the expected number of particles in the set A at time t is given by the integral of qt of xy over the set A. Now, I also want to introduce the additive martingale. Recall that n of t is the number of particles at time t, and I'm going to let x1 of t, x2 of t, and so on denote the positions of the particles at time t. We'll take a real number lambda, and then I'll define y lambda of t to be this sum here. So we're taking a sum over all of the particles at time t, and the contribution to the sum from a particle located at x is proportional to e to the lambda times x. So if lambda is positive, we're giving more weight to particles that are to the right of the origin. Keen showed that this process y lambda is a martingale, and we can prove this using the many-to-one lemma. So suppose we start with one particle at x, and then we can calculate the expected value of y lambda of t. We just integrate the density, qt of xy, against this function here. And then qt of xy is e to the t times pt of xy. The e to the t cancels this e to the minus t that we have here. And so we just get pt of xy times this exponential. And now just from the formula for the moment generating function of the normal distribution, one can calculate that this is exactly equal to e to the lambda x, which is exactly y lambda of 0. So the value at time t, the expected value at time t, is exactly the value that we started from. Now it follows from the branching property and the Markov property that conditional on everything that the process does up to time s, the particles after time s evolve independently, just as independent branching Brownian motions. And consequently, it follows from this calculation that the expected value of the process at time t, given the information up to time s, is exactly the value of the process at time s, and that's the martingale property. Now, because y lambda is a non-negative martingale, the martingale convergence theorem tells us that it converges almost surely to a limit as t goes to infinity. And we'll call that limit just y lambda. It turns out that if the absolute value of lambda is strictly less than the square root of 2, then this martingale is uniformly integrable, and the limit random variable y lambda is almost surely strictly positive. However, if the absolute value of lambda is greater than or equal to the square root of 2, then the martingale is not uniformly integrable, and the limit random variable is almost surely 0. I'm often interested in this more critical case where lambda is equal to the square root of 2, and because the additive martingale just gives a limit of 0, we often a different martingale instead. So we're going to define z of t to be this sum here, and it's possible to show that z is also a martingale. And it's known as the derivative it's known as the derivative martingale because one can obtain the value of z of t by taking the negative of the derivative of the value of y lambda of t with respect to lambda and evaluating that derivative at the square root of 2. This martingale also converges to a limit, which I'll call z, and this time the limit random variable is strictly positive with probability 1. Now we should think about this limit z of the derivative martingale as measuring how much the branching Brownian motion grows in its early stages when we give additional weight to particles that are far to the right of the origin. It is similar to the random variable w that we get in the limit from the Keston-Stigam theorem for ordinary branching processes. Once again, it's a random limit. And it has to be a random limit because, for example, if the initial particle quickly branches into 2, then z has to, on average, be twice as large as it would be otherwise. So z there is a random limit, but after a while, we have enough particles that we do start to get law of large numbers type behavior, and as a result, the derivative martingale will settle down to a limit. Now, it's also possible to get this same limit from the additive martingale under a different scaling. Idacon and Shi show that if we take the square root of 2 times the value of the additive martingale at time t, that will converge to a constant times this random variable z, and an alternative proof of that fact was given by Buteau and Maillard. So I want to move now to describe some of these famous results on the location of the rightmost particle. And I want to begin just by calculating the expected number of particles above some level, which I'll call A. So to calculate the expected number of particles that are above A at time t, we simply have to integrate the density qt of 0y, because we're starting with one particle at 0, from A to infinity. So qt of 0y, that's e to the t times this Gaussian density. And using standard Gaussian tail estimates, this integral is approximately the square root of t over a times the square root of 2 pi times e to the minus a squared over 2t. So one can make that calculation, and then one can also use this expression to see that if a is the square root of 2 times t minus 1 over square root of 2 times the log of t, then this expectation is going to converge to a constant as t goes to infinity. And therefore, as a consequence of Markov's inequality, one can see that the median position of the rightmost particle cannot be larger than the square root of 2 times t minus 1 over 2 root 2 log t plus a constant. Turns out that this is not the right estimate for the median position. What happens here is something that happens quite often in the study of branching Brownian motion, which is that the expected behavior is not the same as the typical behavior. The expected number of particles above this level is of order 1, but the actual number of particles above this level is 0 most of the time, but it's very large with very small probability. So in a typical realization of the process, the position of the rightmost particle is not quite this far away from the origin. In 1983, Bramson showed that in fact, the median position of the rightmost particle is the square root of 2 times t minus 3 over 2 root 2 log t plus a constant. And so to get the correct value for the median position in a typical realization of the process, or for the position of the rightmost particle in a typical realization, we need to replace the 1 that we had on the previous slide by a 3 here. Now, a few years later, Lally and Selke obtained a more precise result. Again, we'll let r of t be the position of the rightmost particle at time t. And they showed that the probability that the rightmost particle at time t is less than or equal to the median position plus x is given by the expected value of e to the minus c times z times e to the minus root 2x. So here c is a constant and z is the limit of that derivative martingale. And the way we can think about this result is that conditional on the limit z of the derivative martingale, the asymptotic distribution of the position of the rightmost particle is the Gumbel distribution, but it's shifted by this multiple of the derivative martingale. If the branching Brownian motion expands very rapidly at the early stages, then it's more likely to have a particle that's very far away from the origin at much later time. And then finally, in 2013, two groups of researchers, Arguin, Bovier, and Kissler, and Idacon, Beresticki, Brunet, and Shi, obtained a much more precise picture of what the branching Brownian motion looks like near the rightmost particle. So they defined this random measure, it's a random point measure psi t. And so they placed a unit mass at the location of each particle minus the median position of the rightmost particle. So here by delta sub x, I mean a unit mass at x. And by subtracting m of t, what we're doing is we are shifting the axes so that we're focused on the position where we should find the rightmost particle. And then they showed that as t goes to infinity, these random measures psi t converge weakly to some limiting measure et rather, the et converge to this limiting measure e. And this limiting measure e is a so-called cluster point process. And to construct that limit, conditional on the limiting value of the derivative martingale, we can consider a Poisson point process whose intensity is a constant times z times e to the minus root 2x dx. So these are the black points in this picture here. And they're all descended from different ancestors near the very beginning of the process. However, each of these particles will have offspring very close to time t, and those offspring will land at nearby positions. And so these points p sub I are actually the rightmost point in a cluster of points. And we can view those clusters of points as themselves being independent point processes on the negative real line with some distribution, say nu. In recent years, other researchers have found that these sort of so-called cluster point processes arise not only in connection with branching Brownian motion, but in connection with a number of other so-called log correlated Gaussian fields. And it would certainly be possible to give a whole series of 5 lectures like this just on those results. But what I'm going to do instead is to turn our attention now to the process that we want to study in much greater depth, which is branching Brownian motion with absorption. So I'll remind you here of the definition, which I think we stated last time. So we begin this time with some configuration of particles to the right of the origin. Each particle independently moves according to standard one-dimensional Brownian motion with a drift of negative rho. So the particles are drifting towards the origin at some rate. Each particle splits into 2 particles at rate 1. It's possible here to consider more general offspring distributions. Most of the results that I'll discuss will still be valid, but I'm going to stick to this simple case of binary branching. And then particles are killed if they reach the origin, and that's what we're using to model selection. So here's a picture of the branching Brownian motion with absorption. Again, we start with one red particle at time 0. It moves according to branching Brownian motion with a negative drift for an exponential 1 time. Then it splits into 2 particles, and those particles also evolve as independent Brownian motions with drift until they divide, and that process continues. Now, in this picture, some particles, including the blue particle here, hit the origin and are killed, but there are still some particles that are alive at the end of the picture. Now, perhaps the most basic question that one can ask about branching Brownian motion with absorption is whether the process dies out or whether it survives forever. And Keston answered this question in his original 1978 paper on branching Brownian motion with absorption. Keston showed that if the drift to the left is greater than or equal to the square root of 2, so that particles are drifting fairly rapidly towards the origin, then the process almost surely goes extinct. But if the drift to the left is less than the square root of 2, then with positive probability, the process survives forever. So there are really 5 different cases that one can consider. We have the supercritical case, where the drift is less than the square root of 2. There's also the slightly supercritical case, where we can write the drift as the square root of 2 minus epsilon, so it's just slightly less than the square root of 2, and we can think about a limit as epsilon goes to 0. Then we have the critical case, where the drift is equal to the square root of 2, and likewise one can consider the subcritical case or the slightly subcritical case. Now, we are going to be most interested in using branching Brownian motion to model populations undergoing selection. And these populations we want to think of as having roughly fixed size. And so for that, we need something close to critical. But because the process dies out in the critical case, it turns out that it's going to be the slightly supercritical case that's most relevant for modeling populations undergoing selection. And that's the case that we're going to deal with in depth in the next lecture. In this lecture, I'm going to focus mostly on the supercritical case and on the subcritical and slightly subcritical cases. Before we focus on any particular case, I want to state a few tools that are useful for studying branching Brownian motion with absorption in general. And a natural place to start is with moment calculations. We would like to be able to compute the expected number of particles alive at time t, or the expected number of particles in a particular set at time t. And there are some standard tools available to make those calculations. So let's consider first just a single Brownian particle started at x with a drift of minus rho and absorption at 0. And then the density for the position of this particle at time t is given by this formula here, where density is in quotes because the integral of this expression is strictly less than 1, since the particle may be absorbed at the origin before time t. So this first term is just the density of ordinary Brownian motion. This second term is a term that we subtract to account for the absorption at the origin. This can be computed using the reflection principle. And then we have a Gersonov factor, which accounts for the drift. And now we want to add branching at rate 1 into this process. And so we will let qt of xy be e to the t times pt of xy. And the Manytotwo lemma that we discussed earlier tells us that it's this function qt of xy which describes the density for branching Brownian motion with absorption. So in particular, let's suppose we want to calculate an expectation like this. So we are summing up the values of the function f at the locations of the particles at time t, and then taking the expectation. And this is equal to the integral of the function f with respect to qt of xy. And one can take f to be the indicator of the function a to see that the expected number of particles in the set A is then given by the integral of qt of xy over the set A, which is how we want to think about the density for the process. One other thing to note here is that this expression is equal to e to the t times the expected value of f of b of t, where b is Brownian motion with a drift of minus rho and absorption at 0. And here we have to think of f of b of t as being 0 if the Brownian particle is absorbed before time t. And so the point here is that we can calculate expected values about branching Brownian motion by making calculations that involve just a single Brownian particle. And that's why this result is called the Manytotwo lemma. Here is the formula for the density that we just obtained. And it'll be instructive to think about what happens if we let time go to infinity while keeping x and y fixed. So as t goes to infinity, these exponents become small. And so we can approximate e to the minus z by 1 minus z. And if you do that approximation and you do a little bit of algebra, we see that qt of xy is asymptotically given by this expression here, where by this symbol here, I mean that the ratio of the two sides tends to 1 as t goes to infinity. And then we can also integrate this right-hand side over y from 0 to infinity to get an asymptotic expression for the expected number of particles at time t. So what can we learn from examining these formulas? So one thing to observe is that the formula for qt of xy is proportional to y times e to the minus rho y. And so this is telling us that no matter where the initial particle is located, the density of particles near y after a very long time is roughly proportional to y times e to the minus rho y. Also notice that both of these formulas are proportional to x times e to the rho x. So we can think of x times e to the rho x as telling us something about how many descendants a particle at x is likely to have alive a long time into the future. Also notice that this exponent is going to infinity if rho is less than the square root of 2, and it's going to 0 if rho is greater than the square root of 2. If rho is equal to the square root of 2, this exponential is 0, but then this t to the 3/2 down here tells us that the expected number of particles at time t goes to 0 as t goes to infinity. So we see that the expected number of particles is going to 0 if and only if rho is greater than or equal to the square root of 2. And that, of course, is very consistent with Keston's result about when the process goes extinct. All right, so far we've only looked at first moment calculations, but it will also be very useful to be able to make second moment calculations, which are useful for controlling the fluctuations of the process. And so here is a theorem which goes back to the early work on branching Markov processes due to Ikeda, Nagasawa, and Watanabe. So we want to calculate the expected value of this square. And when we expand out this square, notice that we get a sum over pairs of particles. And in order to end up with particles at the locations y1 and y2 at time t, there has to be a branching event at some earlier time s where the trajectories of these two particles diverged. And so a particle has to go from x to some location z in time s. A particle has to go from z to y1 in the remaining time t minus s. And then the other particle produced at the time of this branching event has to go from z to y2 in time t plus s. And so if we integrate that against the time s of the branching, the location z of the branching, and the locations y1 and y2 of the two particles, we do get a formula for this second moment. But there's also another way of writing this formula, which is known as the Manytotwo lemma. So let's consider two processes, B1 and B2, which evolve as Brownian motion with a drift of minus rho and absorption at the origin. And let's assume that these two particles move together for an exponentially distributed time with rate 2. And then after that time, they move independently. So then it turns out that this right-hand side here is exactly equal to this expectation. Basically, the first term accounts for what happens if the two particles stay together until time little t, and the quadruple integral evaluates this expectation on the event when the particles split before time little t. And so again, the basic point is that in principle, one can calculate this second moment by making a calculation that just involves two Brownian particles. So that's why it's called the Manytotwo lemma. And there's even a generalization due to Harris and Roberts called the Manytofew lemma, which generalizes this idea to kth moments. So next, I want to introduce a useful martingale that's associated with branching Brownian motion with absorption. Let's define v of t to be this sum here. So we're summing over all particles at time t, and the contribution to the sum from a particle located at x is proportional to x times e to the rho x. And one can show that this is a martingale using the same technique that we discussed before. Imagine starting from one particle at x, use the density to calculate the expected value of v of t, and what you're going to get is exactly v of 0, and then the martingale property follows from the branching property and the Markov property. Now, because this is a non-negative martingale, it converges almost surely to a limit which I will call v. Of course, if the drift is greater than or equal to the square root of 2, the branching Brownian motion is going extinct. So this limit v has to be 0. However, in the supercritical case where the drift is strictly less than the square root of 2, John Harris and Simon Harris showed that this martingale is uniformly integrable. And on the event of non-extinction, this limit random variable v is almost surely strictly positive. All right, so let's now look in more detail at the supercritical case where the drift is strictly less than the square root of 2. And let's imagine that we start with just one particle located at x. So here's a theorem which gives a pretty good understanding of the long-run behavior of the supercritical process. So on the left-hand side here, we have n of t, that's the number of particles at time t, and we divide it by the expected number of particles at time t. And this result tells us that as t goes to infinity, this ratio converges to a limit, which is given by the limiting value v of the martingale that we discussed on the previous slide, divided by xe to the row x, which you can understand as just being v of 0. So the limiting value v of that martingale tells us about, in the long run, how many particles are going to be alive. So interested in where the particles are located. So let's let nu be the probability measure on the positive real line, whose density is given by rho squared times y times e to the minus rho y. And on the left-hand side here, what we have is the empirical distribution of the locations of the particles at time t. So we put a unit mass at the location of each particle, and we divide by n of t so that we get a probability measure. And this result shows that almost surely on the event of non-extinction, these random probability measures converge weakly to the probability measure nu that was defined here. So in the long run, no matter where the position of the initial particle is, the particles start to distribute themselves according to this measure nu. And this is really what you would expect from seeing the asymptotic formula for the density qt of xy. Now, Keston stated the result very similar to this one in his original 1978 paper on branching Brownian motion with absorption, but he did not publish a proof. Instead, he just wrote, "So far we have only an ugly and complicated proof," and he left it at that. But a couple of years ago, Louis-Dor and Saglietti did provide a complete proof of this result. Now, I do want to explain how they carried out that proof, because some of these ideas will be important later on. I'm going to let nt of A be the number of particles in the set A at time t. The main idea of what we want to try to do, I should mention first that it's sufficient to study these quantities nt of A, because this gives us information both about the total number of particles and about the distribution of where the particles are located. So what we want to do in principle is to calculate the expected value and variance of these quantities nt of A. And we know how to do that because we just explained how to do first and second moment calculations. And then one would like to show that the variance of nt of A is much smaller than the square of the mean. So that would tell us that the number of particles in the set A is highly concentrated around its mean, and one could just apply Chebyshev's inequality to arrive at a limit theorem. Now, the problem is that it's not actually true that the variance of nt of A is much smaller than the square of the mean, and that's a consequence of the randomness at the beginning of the process. It's the same problem that we've discussed before. For example, if the initial particle branches into 2 right away, then one would expect the number of particles in the set A after a long time to be twice as large as it would be otherwise. So this randomness at the beginning of the process prevents us from getting this kind of a concentration result. So what we have to do instead is to fix some large positive time s, and then we calculate the mean and variance of the number of particles in the set A at some much later time t, conditional on everything that happens up to time s. Now, the expected number of particles in the set A, conditional on fs, is going to be roughly proportional to the value of the martingale v of s. And if we take s to be large, that's going to be approximately equal to v. Furthermore, if we take S to be large enough, it will be true that the conditional variance of nt of A is much smaller than the square of the conditional mean. Basically, once we get past the randomness that occurs at the beginning of the process, we do start to see a law of large numbers type behavior, and the number of particles in the set A will be close to its conditional expectation.
Sorry, Jason, I'm
Yes.
confused about the second last bullet point. So that it's proportional to V of S. Shouldn't that depend on A?
Yes, it's also proportional to A, but in the long run, as t goes to
Oh, I
infinity,
see,
you're
okay.
going to see it'll basically be like
See, but-
something, you know,
okay.
V of S times nu of A times
I
some
see.
constant.
Okay,
Yeah.
thanks.
Now, there's still one further complication, which is that argument that I just outlined only works when the drift rho is strictly less than 1. When rho is greater than or equal to 1, Jonquière and Saglietti showed that convergence in L2 fails. And as a result of that, it's not true that the variance of the number of particles in the set A is small relative to the square of the mean. The problem here is something that happens quite often, again, in the study of branching Brownian motion, which is that we have that in this regime, the second moment is dominated by rare events. And what happens in these rare events is that one particle gets unusually far from the origin, and that allows it to have many descendants that survive because they're able to avoid being killed at the origin. And that's enough to cause the second moment to explode. And so the solution to this kind of problem is usually to do some sort of truncation. And what the authors did in this case was that they considered a modified version of the process in which particles are killed if they reach this curve. So at time u, we kill particles if they hit the origin, but we also kill particles if they hit some large constant times 1 plus u to the 3/4. And then one can make a first moment calculation to show that this truncation does not have very much effect on the expected number of particles in a particular set A in the long run. And consequently, Markov's inequality tells us that we can basically ignore the particles that are lost due to truncation. And then for this truncated process, the variance of the number of particles, the conditional variance is very small relative to the conditional mean, and the argument proceeds as it did before. Okay, so let's move now to the subcritical case where the drift is greater than the square root of 2. Again, we'll start with one particle at x, and in the subcritical case, the process goes extinct, and we're going to denote by zeta the extinction time. Now, in 2007, John Harris and Simon Harris proved a result about the probability that they got very sharp asymptotics for the probability that the process survives for an unusually large time t. They showed that the probability that the process survives for at least time t is asymptotically a constant over the square root of 2 pi t to the 3/2 times x times e to the rho x plus 1 minus rho squared over 2 times t. And here by this symbol, again, I mean that the ratio of the two sides tends to 1 as t goes to infinity. And this is also asymptotic to rho squared k over 2 times the expected number of particles alive at time t. And I should mention that the constant k here depends on the drift rho, but it does not depend on the position x of the particle. Now, from this result, they also deduced a Yaglom type limit theorem for the number of particles at time t conditioned on the event that the process survives until time t. They showed that the expected number of particles at time t conditioned on survival as t goes to infinity converges to 2 over rho squared k. And they also deduced, as a consequence of arguments in Chauvin and Roault, that there is a probability distribution pi j with a mean of 2 over rho squared k, such that conditional on survival past time t, the probability that there are exactly j particles alive at time t converges to pi j as t goes to infinity. Now, what about the slightly subcritical case? So let's say the drift rho, we want to write now the drift rho as the square root of 2 minus 2 epsilon. And we want to think about what happens if we take a limit as epsilon goes to 0. Again, we'll start with one particle at x. And here's a theorem that was recently proved by my graduate student, Jiaqi Liu. She showed that there are positive constants C1 and C2, such that if epsilon is sufficiently small, then the limiting expected number of particles at time t, conditioned on survival at time t, is bounded below by e to the c1 over the square root of epsilon, and bounded above by e to the c2 over the square root of epsilon. We believe, however, that this conditional expectation is probably dominated by rare events where the number of particles alive at time t is unusually large. And we believe that conditional on survival until time t, in a typical realization, the logarithm of the number of particles will be of order epsilon to the minus 1/3, rather than order epsilon to the minus 1/2, which would seem to be suggested by this theorem about the expectation. So finally, I want to comment on how this result in the slightly subcritical case is proved, mostly because this will allow me to introduce an idea that is widely used in the study of branching Brownian motion, but will not come up again in these lectures, and that is the spine decomposition. So recall that we have this martingale v that we defined earlier, and if we were to divide it by v of 0, that would give us a mean 1 martingale. Now, anytime we have a non-negative mean 1 martingale, one can use it to define a change of measure. So let's define a new probability measure qx, such that the Radon-Nikodym derivative of qx with respect to the original probability px, restricted to the information in the branching Brownian motion up to time t, is given by v of t over v of 0. So then one can ask, how does the branching Brownian motion evolve under this new measure q? Well, it turns out to evolve in the following way. So there's a distinguished particle, which is called the spine, which evolves as a 3-dimensional Bessel process started from x. So the 3-dimensional Bessel process is the distance from the origin of 3-dimensional Brownian motion. And it can also be interpreted as 1-dimensional Brownian motion conditioned to avoid the origin. So in particular, this spine particle never gets killed at the origin, and instead it survives forever. The spine gives birth to new particles at rate 2. That's twice the rate of ordinary particles. And then particles that branch off the spine behave exactly like ordinary particles. They just initiate new copies of branching Brownian motion with drift. And one reason why it's useful to study this spine decomposition is this result here, which says that if A is any event that is determined by the evolution of the branching Brownian motion up to time s, then the probability of the event A, conditioned on survival at time t, converges as t goes to infinity to the probability of A under this new measure q. And so studying the Yaglom limit, that is the behavior of the branching Brownian motion conditioned on survival for a long time, is in some sense equivalent to studying this spine decomposition under the new measure. I recall from the result of Paris and Paris that if we want to calculate the expected number of particles alive at time t conditioned on survival until time t, we need to calculate this constant k, which it turns out can be written in this form here. And the way we make use of the spine decomposition is that we can use this change of measure to write this probability of survival past time t as the expectation under the new measure q of v of 0 divided by v of t times the indicator of the event that the process survives past time t. V of 0 is equal to x times e to the row x, so we get some cancellation there, and we end up with the result that k is equal to the limit as t goes to infinity of the square root of 2 pi times t to the 3/2 times the expectation under q of the reciprocal of this sum. And then we can use what we know about the behavior of the process under the spine decomposition to estimate the expected value of that sum. Now that leads to some rather tedious technical estimates, but we are able to estimate that expectation well enough to prove the result that we stated earlier. So that's everything that I wanted to say about branching Brownian motion in the supercritical, subcritical, and slightly subcritical cases. In the next lecture, we will move on to the slightly supercritical case, which is the most relevant for describing populations undergoing selection. And I'll stop here for today. Thank you.
So thanks very much, Jason. Does anyone have any questions? Oh, lots of questions. Okay.
Is the spine, it's a Bessel 3, regardless of the value of rho, the drift? Is that the case?
Yes, because the change of measure in that martingale has an e to the rho x in it, which is compensating for the drift.
Oh, I see. Okay, thank you.
I was just wondering the convergence of px conditioned on survival to qx, is that true for just rho less than or equal to √2 for any such rho? Or sorry, greater, or which one is subcritical when it's too fast?
As far as I know, that's a subcritical result. I mean, in the supercritical case, conditioned on survival is a very different kind of conditioning, right? It's a much weaker conditioning.
Yeah, because there's a size bias thing that kind of comes in.
Yeah. So
Right.
as far as I know, that's a subcritical result.
Okay.
And are there any questions in the online audience? And also, people online should feel free to just speak up if they want to, and we'll hopefully hear you in here. So I also had a question about the result. It was quite near the end about the slightly subcritical case, where you said that you had this conjecture that you would see, that log of nt would be order of epsilon to the minus a third rather than. So is it possible for you to explain to us why you think?
Yeah, a little bit, although it's based partly on ideas that are going to be in the fourth lecture. But
okay.
Nevertheless, if you go back here, you see we have pretty precise asymptotics for the probability that a process survives past time t. It allows you to calculate what's the probability of surviving for time t plus s conditional on survival until time t. So we basically know, conditioned on survival past time t, how long the process should typically survive for. And the problem is that if we have kind of a particles in what you would think would be a natural configuration, and you had e to the constant over root epsilon particles, basically that would survive longer than it's supposed to. And so that just doesn't seem like it can be right.
Okay.
This does seem like it can be right.
Okay, interesting. But you sort of don't have you don't have an idea, like that doesn't give you a technique to prove it, or could that turn into a proof?
We're going to be discussing that this week.
Okay, sorry.
But I should also add that the result about the expectation, though, still has value, because that constant k is showing up, for example, even in the formula for the asymptotic survival probability. So even though the expectation is different from the typical value we think here, there's still, I mean, that the formula for the expectation is still relevant by itself.
Any more questions, or people online? I'll give you a bit more time to. Okay, well, I think we're sort of